Welcome to the survey of the elementary principles in classical mechanics. Today we are going to continue discussing exercises, and we will begin with a problem involving drag forces and free fall. The statement is as follows. Obtain the equation of motion for a particle falling vertically under the influence of gravity when frictional forces obtainable from a dissipation function k over 2 times v squared are present. Integrate the equation to obtain the velocity as a function of time and show that the maximum possible velocity for a fall from rest is v equal n times g over k. The Lagrange equations of dissipation are written in the general form here, and our single generalized coordinate will be the height z. Then the kinetic energy and potential follow immediately with their well-known expressions. So the Lagrangian itself is given by the result here, and the dissipation function is of the standard form we have already discussed, velocity dependent, and as such the partial derivatives involved in the equation of motion are all listed here, and the result is the boxed one labeled with the number 1. To solve this equation, we set the time derivative of z to be equal to some function of time f of t minus m times g over k. And if we put this in equation 1 and work things out, we get to the result here, and finally the differential form that's been written here. So this can be integrated immediately, and the result up to some integration constant is the one here. So the natural logarithm of f is minus k over m times t plus this constant. So the function itself will be some constant c times an exponential of argument minus k over m multiplying time. Remember that the time derivative of z must be equal to this result minus mj over k. And if I want the initial velocity to be 0, then using this condition on the above result, I obtain for the integration constant the value mg over k, and as such, the final result concerning the velocity of the particle is the one here. It's mj over k, mg, over k, multiplying the exponential of minus k over m times t minus 1. And now if we consider the limit when time goes to infinity, then this exponential goes to 0, and as such the result is the one here. This is the value of the terminal velocity. It has a minus sign because the particle is falling, so the z coordinate is going from its initial maximum value, it's going to 0, and as such the magnitude of v is just m times g over k. And as an illustration, I've considered in this result that the ratio of m over k is simply equal to 1. And then you can see that the velocity in meters per second as a function of time in seconds looks like the curve traced here. So we see that in about 5 seconds we have reached the terminal value of the velocity for the set of parameters. So as such, what infinity means in mathematics can be very different from what happens in reality, as in this case infinity is equivalent to just a few seconds of falling through the atmosphere. And for the last problem of this set, we are going to discuss the dynamics of a spring pendulum. The statement is as follows. A spring of rest length LA is connected to a support at one end and has a mass M attached at the other. Neglect the mass of the spring, the dimension of the mass, and assume that the motion is confined to the vertical plane. The spring stretches without bending and can swing in the plane. Using the angular displacement of the mass from the vertical and the length that the spring has stretched from its rest length, find Lagrange's equations. Solve these equations for small stretching and angular displacements, plot the results in a single graph. Solve the equations in part A to the next order in both stretching and angular displacement. Discuss the motion using some reasonable assumptions about the spring constant, the mass, and the rest length. Is resonance likely under the assumptions stated in the problem? Consider the spring to have a total mass m, which is much smaller than capital M. Neglecting bending, set up Lagrange's equations correctly to first order in M. Alright, so I will denote by L1 the quantity being equal to L0 plus L, where L1 is the total length of the spring at a given time. L0 will be the equilibrium length, be it under its own weight or that of an attached mass, and L is the stretching or contraction of the spring. We begin by working out the dynamics of the spring under its own mass m. So first of all, I wrote here Hooke's law for an element of length of the spring, and I want this force to be equal with the force of gravity of the whole mass of the spring that's hanging on top of this length element. So I'm assuming that this gravitational force increases linearly with the length that is on top of the element for which I'm currently calculating. And then I am also going to assume that the spring's density remains constant throughout in spite of the deformation. So as such, I can write uh, the element of mass as in the following way. I can introduce a constant density times z dz, and then I can obtain the result here, where so I'm implicitly assuming that the density is just the ratio of mass to the total length of the spring. And then if I integrate this equation on the left hand side, I integrate for the total stretch under the spring's own weight, and on the right hand side I integrate for the total length of the spring. I obtain the result here. So the quantity L is the amount of stretching the spring undergoes in a gravitational field under its own weight. It's just m times g over 2 times k. And the equilibrium length is the one here. It's the rest length of the spring. So if the spring is, let's say, resting on a horizontal surface, and to which I must add this quantity. And let's see. Now we calculate the energy of the spring oscillating freely with no attached weight. So I will have a radial component of the kinetic energy, for which I must consider that the squared velocity is not going to be equal for each element of the spring. So the elements towards the free tip of the spring tend to oscillate faster than the elements towards the uh, attachment point. So I need to take this squared velocity and integrate it over the total mass of the spring, assuming that it varies with each mass element. So once again, I am stating that the density is assumed to be constant, which allows me to write the expression as given here. And then I will assume that the velocity of each element increases linearly with the length of the spring up to some maximal value, which is L dot. So with these considerations, the radial part of the kinetic energy becomes the integral here, which is very easy to solve and leads me to this expression. So the radial kinetic energy as a function of mass is 1 over 2 L dot squared times m over 3. So effectively only a third of the spring's mass enters the formula of the radial kinetic energy. Quite similarly, I can work out the kinetic energy of the angular motion. Here it's a bit easier because the spring will rotate as a whole about the vertical. It's not allowed to bend in any way. So the mass integral is simply written like here, and the result is very similar in structure to what was previously obtained. Once again, the effective mass entering the formula is m over 3, and then the potential energy is given simply by the expression here. So it's the position of the center of mass of the spring, uh, taking into account the deviation from vertical, and it's chosen in such a way that when the spring is horizontal, the value is maximal, it's 0, and when it's hanging on the vertical, I obtain the minimal negative value of the potential. So with these results, we can write the Lagrangian for the spring moving under its own weight as containing the total kinetic energy of the spring, the potential energy of the spring, and the elastic energy derived from the fact that it's allowed to oscillate in length. Adding the mass m to the end of the spring shifts the equilibrium position to the new value here. So it's the initial equilibrium to which I must add capital M times g over k, and this follows immediately from Hooke's law. If you calculate the stretching of the spring with the addition of the new weight, and then the total length of the spring is just this quantity lb plus the stretching at a given time L, and the coordinates of M can be written very simply in terms of the spring's total length and the orientation with respect to the vertical axis. I can then calculate the time derivatives and the squared velocity, and as such the total Lagrangian becomes the one here, where I've included, so there's a kinetic term for the spring itself, then there's the kinetic term of the mass, and then there's the potential term, the gravitational potential term, both for the spring and the mass, and the elastic energy of the spring itself. Then for the stretching, it's straightforward to calculate the derivatives. And in order to set up the equation of motion, I will use the following notations. Because I want to emphasize the spring's mass, I will denote the equilibrium position as being LA, the free spring, plus the stretching caused by the mass attached at its end. And I will use the following Taylor expansion. So for expressions such as this, if I'm dividing the equations by this quantity, if I do a Taylor series under the assumption that the ratio of m over capital M is much smaller than 1, then to first order I obtain the result here. And as such, the differential equation for the stretching is the one here. And we can see that it's a nonlinear equation due to the product between L and phi dot squared, and of course the presence of the cosine of phi. Now for the angular equation, uh, the partial derivatives are calculated easily enough, but the final result is a bit more involved. So using the same kind of approximation for this term, you can find the result written here. So it looks a bit messy, but what I did was isolate terms of this form throughout, which is what I'm assuming they wanted with the initial statement of the problem. In the original formulation, they suggested using an analytical computer program for this step, but I don't really see the point, assuming that this calculation is correct. It's something that's simple enough to do in spite of being a bit tedious in isolating these terms with care. In any case, we see that again it's a highly nonlinear equation, And now we are going to simplify matters both in this result and the previous one involving stretching. So what we will do is that we will neglect the ratio of m to capital M, and we will let L1 be equal to L0 plus the stretching L, where L0 is once again the rest mass of the spring plus the stretching caused by the mass attached to its end. And then the equations of motion will reduce to the expressions 1 and 2 written here. And to simplify things further, we will assume small amplitude vibrations and retain only the linear terms. So no products of functions involving stretching and uh, angular displacement are allowed, and no higher order terms are allowed in terms of power, so these quantities and so on. So for the stretching equation, this implies that we neglect the squared term here, and we are assuming that the angular motion is small enough that the cosine of phi can be approximated with 1. So this is just the first term of the first order term of its Taylor expansion, and therefore equation 1 is reduced to the harmonic equation here, where for the frequency omega 1 being equal with the square root of k over m, the solution is the one given here. So it's a sine of omega 1t with an amplitude a and a phase delta 1. For the angular equation, the low amplitude conditions will imply that L1 is essentially L0, so it's the equilibrium length of the spring. This product is 0, and sinus of phi is equal to the angle phi. And in these conditions, you can show that equation 2 reduces to the simple harmonic equation here for the frequency omega 2 being equal with the square root of g over L0. And as such, the solution is phi as a function of time equal with a sine of omega 2 times t, having an amplitude b and a phase delta 2. Now, as an example, I will consider that the rest length of the spring is of 10 centimeters. And I will want, by T2, I am denoting the period of its angular motion, and I want this to be equal with 2 seconds. And with T1, I am denoting the period of its radial oscillation, and I want this to be T2 over 10. And I will set the following initial conditions. So the initial stretching, I want it to be twice capital M times G over K, and I want the initial angle to be given by the value here, pi over 18. This should be about 10 degrees, and I will assume that both the initial radial and angular velocities are 0. And in this case, the result, the solution of those equations is plotted here. The solutions are plotted here. So L, the stretching given in centimeters, is the continuous line, and the angular displacement given in radians multiplied with 100 is the dashed line, both as a function of time. And what we observe is, of course, just simple harmonic motion independent in the two coordinates. Now, to write the radial equation in second order, we make use of the following approximations. The quantity here reduces to L0 times phi dot squared, because the product between this and this would be a third order term. G cosine of phi is given by the expression here, which is just the second order Taylor expansion of cosine of phi. And I will also employ this change of variables briefly to eliminate this quantity from the equation. But once that is done, I will drop the primed index and revert to the L notation. And with all these things put together, the result in second order should be the one here. And for equation 2, we use the fact that in second order sinus of phi is still equal to phi, and we use the second order Taylor expansion of 1 over L1, which is going to be the quantity here. And with all of these things, we can write the angular equation as the boxed result labeled with 4. Now, to solve the equations in second order, we assume that the nonlinear terms are small and have a perturbative effect on the harmonic motion. So we formally write the two solutions um, as powers of a parameter epsilon, and we retain only the first and second order term, where in first order the coefficients are L0 and phi0, which are just the solution of the harmonic equations we previously discussed, and the second order solutions f and g are currently unknown. The idea is to insert the general solutions for L and phi in the second order equations 3 and 4, equate all the terms into coefficients multiplying the powers of epsilon, and truncate the equations at epsilon squared. The first order coefficients will vanish as they are the solutions of the first order harmonic equations, and we then equate the coefficients of epsilon squared to 0. This is very straightforward, but it's also a very lengthy calculation, so I've just outlined the general idea and I will present the results. So this approach will lead to the following equations for f and g. We obtain the results here for the two unknown functions. And now we consider that, okay, so this was a bit of an unfortunate notation. Uh, do not confuse the function g with the gravitational acceleration. So you can use, for example, an x and y, let's say, to or some other, or u and v, some other combination of letters, but it should be clear enough that this, yeah, the left hand side here is a function, and this is just the parameter, the gravitational acceleration. But in any case, the harmonic solutions are linear combinations of trigonometric functions. So I've written the previous result, but in a more general form for L0 and phi0. And if, for example, we insert these solutions into the equation for f, into the result here, we obtain an equation of this form. So we've managed to turn what was a nonlinear expression into a linear one, involving trigonometric functions and the coefficients alpha, beta, and gamma given in terms of the parameters of the system, namely the gravitational acceleration and the integration constants that can be obtained from initial conditions. And then we can seek a solution of this equation of the general form here. And we equate the coefficients once again to obtain the values of a, b, and c. And then the final result in second order will simply be the one stated here. So for the function L, we will have L0 the harmonic solution, and the function f is going to be the one given here. So notice that even though it is the solution of the radial motion, it involves the frequency of the angular motion. And also notice that this solution is problematic when this denominator approaches 0, which is something that we will discuss in more detail later in the problem. And in a completely analogous manner, we obtain the second order solution for phi. So it's the same kind of calculation, very straightforward but a bit lengthy, which gives us, we know phi0 as a simple harmonic solution of the first order equation, and the function g is the one given here in terms of the equilibrium length of the system, the integration constants that are obtained from initial conditions, and the frequencies of the radial and harmonic motion. And here's the results. It's in the same example that was used for the previous illustration. So I have the same initial conditions, the same parameters of the system, and what I obtain is in second order, I get the second order terms imply a stretching of the order of the millimeters and an angular motion of the order of radians multiplied by 1000. And we see that the stretching is still a harmonic motion. And for the angular motion, I get this noisy pattern, but both of these are of so small amplitude that for that parametrization of the problem, I will essentially never see the second order terms. They can be completely neglected with respect to the first order harmonic motion. However, the second order terms in both solutions exhibit singularities when omega 1 squared is equal to 4 times omega 2 squared. These frequencies correspond to a resonant response of the pendulum, where the nonlinear terms are no longer perturbative, but instead dominate the motion. Near a resonance, the dynamics of the system can no longer be described even approximately by harmonic motion. For this system, the resonance condition reads into the ratio k to capital M being 3 times g over LA. And for spring rest lengths of the order of centimeter, this means that the frequency of the radial motion is about 50 hertz, but this would be for a spring rest length of 1 centimeter. If it's longer, then this drops even more. So it would appear that resonance is very likely in a spring pendulum, which is probably the reason why it's a very studied system when it comes to chaotic dynamics or the transition between order and chaos. And here is an illustration of the situation when I am not that close to resonance as to make the perturbative approach unreasonable, but I am also far enough away from harmonic motion that I can see a significant impact from perturbative effects. So this is the total stretching in both first and second order for in centimeters, and the angular motion if radians multiplied by 100. So what I've assumed here is that I have an higher initial stretching and a higher initial angle of the motion, and I'm assuming that the two frequencies are a bit closer together than they were initially, but still far enough away from resonance so as to let the perturbative solution to have sense. And then you can see that the radial motion is largely still harmonic in nature, but what happens is that now the harmonic oscillation is about an equilibrium point that by itself oscillates with its own frequency, which is the initial harmonic frequency of the unperturbed angular oscillation. And as for the angular motion itself, I see that it is still periodic, but it's no longer quite harmonic in nature, in the sense that what I see here is that the pendulum tends to backtrack periodically over a small distance. So the biggest backtrack that you can see here corresponds to maybe about 5 degrees or so, and it's less towards the end points of the oscillation. And so this would be the result in second order when perturbations are present. And with that, we've made it to the end of this chapter. We began from Newton's second law of motion, and we ended up discussing problems that are not that far away from the realm of chaos. So it would seem appropriate and given the purpose of this introduction and with an eye on future developments, to end with a quote from Newton himself. This is taken from his treatise in optics, published sometime in the 18th century, and it contains questions that were very relevant then and are maybe even more so relevant today. leaving you with them. I want to thank you very much for watching. I hope you found this video worth your time, and I will catch you later. Goodbye.